All right, guys, in order to get to, I told you last week that we would do those last 3 questions, 4 questions together. But in order to get to that, I want to draw some comparisons of stuff that you already know. Okay, so let's say we had an equation that said square root well, let's just start simple, real simple. What if I had 2x equals 6? How do I solve that? Divide by 2. Why? Say it again. Okay, so I'm trying to isolate x. I'm trying to get that by itself. Okay, and that'll be something as we work throughout some other comparisons here that we're going to try to do. Same thing on those last 4 or 5 questions in the homework. Trying to isolate x. Okay, and you guys have probably, why do we divide? What is going on in 2x equals 6 that elicited division? Or told us to use division. What's happening between the 2 and the x right here? Multiplying. So division undoes multiplication, right? Do you guys remember what you call those operations in comparison to one another? They are inverses. Good. A lot of people, I was hoping that, well, I wasn't really hoping, but usually the answer I get with that is that they're opposite operations. You heard that before, right? And you probably in like 6th grade, 7th grade, you start using the phrase opposite operations because what is the opposite of division? Well, multiplication, maybe. Okay, it's more appropriate for addition and subtraction. What's the opposite of addition would be subtraction, right? Opposite, I think, is a poor word. Okay, because when we think about the word, the phrasing that they undo each other, okay, is what we call an inverse operation. Okay, so multiplication and division are actually inverse operations. Okay, if I took 2 times 3 gives me 6. To get back to 2, I'm going to have to divide by 3, right? So I did multiplication to get here. I undo that multiplication with division. Okay, so they are inverse operations. What about something like if I had radical x equals 4? How would you solve for x here? Let's do it this way. Let's do this one first. Let's go x squared equals 4. What would you do there to get x? You would square root. Okay? And that would give me x is equal to 2, right? What undid the power of 2? It was the square root, right? Okay, so square root of x and x squared are inverse operations. Okay? Now, there's certain, and this will be something that you investigate in other algebra classes, there's a certain relationship about what x values we can do this with. Okay? But what if I had x squared, I'm sorry, we already did that. Let's go square root of x, going back this one. What would I have to do here to get x out of the radical? I would have to square it. Okay? And squaring is the inverse of the square root. So when we say inverses, that means one undoes the other, and the other undoes the first one. Does that make sense? It's a two-way street with inverses. Okay? Let me show you something graphically here for inverses. And this is what I was talking about with the square root function. The square root function actually doesn't have an inverse for this. So x squared does not have an inverse, okay? Because, you guys remember talking about functions? You guys ever talk about the vertical line test? Okay, so this thing's a function because it passed the vertical line test. The definition of a function is just a unique equation, a unique relationship. And it basically says to be a function, you have to have, for every x value, there is one and only one y value. So if I tell you, everybody look at the x value of 2, Look at the x value of 2. Everybody's going to spit back to me the y value of 4. Does that make sense? So this thing is a function. Okay? Now the inverse of every function is the reflection across that line right there, y equals x. So it actually makes it a little bit easier for me to demonstrate this in GeoGebra than there. So let's go. So we got x squared, that graph there. I put y equals x in. Okay. Now if I reflect that graph there, and I get this second green graph, and I'm going to make it blue. Does that blue graph pass the vertical line test? No. So it's not a function. Okay? And what that tells me right now is that x squared was a function. If x squared has an inverse, then x squared inverse also has to be a function. Well, this isn't a function, so this cannot be the square root of x, essentially. Okay? What this is, if I type in square root of x, you see how it gives me that part right there? Negative square root of x gives me that bottom part. Okay? So in order for x squared to actually have an inverse, actually, I'm going to say if x is greater than 0, then graph x squared. We have to just graph that part of it. Okay? Because here's the reason. A square root is a symbol for a number that when I multiply it by itself, I get the radicand. Is there a number that I can multiply by itself to get negative 4? Because my options are positive 2 times positive 2, right? That doesn't give me negative 4. And my other option would be negative 2 times negative 2. But that doesn't give me negative 4 either, right? So when we have values that are negative, we can't take the square root of them. If you type in on your calculator, any calculator you have, and I type in square root of, I'm just going to put a here, but I'm going to choose negative numbers. You see how it says undefined? Okay, we can't take the square root of a negative number because of that relationship that a square root is a symbol for a number times a number. Okay, a number multiplied by itself to give me that. So a negative times a negative is always going to give me a positive number. Okay, so that's the issue with this. Okay, but now if I reflect that across the line y equals x, it gives me that red curve, and that red curve does indeed pass the vertical line test. Does that make sense? And that would be a function. Okay? So, why am I talking about all this? The sine function, the cosine function, and the tangent function, along with the secant, cosecant, cotangent, they have inverses as well. Okay? Now, what I want to go back to and show you is a relationship about these inverses. If I have the point on this graph right here, would you guys agree that the point 2, 4 exists on the gray graph? That was x squared. That's on x squared. 4, 2 should show up on the other graph. Okay? So let's see what we did here with these values. Okay? I should have 3, 9 on that graph, and I should have 9, 3 on that graph. Okay? What is happening with these ordered pairs to go from one graph to the next if they're inverses of one another? I just flip-flop the x's and the y's, right? If a comma b is on f of x, then b comma a is on its inverse. That's the relationship that we get here. That's the nature of being a reflection across the line y equals x. That's what happens. So we can use that. Basically what I'm trying to get at here is that the input on this function, okay, becomes the output on this one. and the output of this function becomes the input on this. Does that make sense? Okay, so we know, so let me write it this way. If I have a function, so our function notation is this, f of x, okay? If, write it this way, if a comma b is on f of x, then b comma a is on f inverse. That's how we read it. That's not an exponent. It's a superscript. It's a notation thing, and we read that inverse, f inverse or inverse of f. But what that means is if this is the input, that's the output. Okay. Down here, this output becomes an input in the other function. And the reason I want to talk about that is what happens with the sine function. When I put the sine here, okay, what have we been putting in here as we use the sine function? What is the argument always? It's an angle, right? Okay. And for the output, it gives us the ratio of the opposite divided by the hypotenuse, right? That's our outcome. Okay. So if that's our original function f of x, okay, the input is an angle, the output is the ratio. If there is an inverse of the sine function, then things should change. So here's the notation that we use. And there's actually a couple different notations. If I go sine, I'm going to put a superscript of -1 because that's inverse. Using this idea up here that the input and the outputs change spots, what is going to go in these parentheses right here? That's the ratio. You put the ratio of the sides, opposite divided by hypotenuse, and the output that it will give you is an angle measurement. And that's what the last 4 or 5 questions on your homework from Thursday were asking you to do. Can you take two angles, well, not two, it's two side lengths, knowing how they relate to one another, are they opposite and adjacent, or are they opposite and hypotenuse, or adjacent and hypotenuse, run them through this function, and it spit back an angle to you. Okay? Now, what we find out, and this is what we get into in college algebra, trigonometry, a lot of this stuff here we talk about in Algebra 2, college algebra. Remember when I said I couldn't take the square root of negative numbers? Okay? I'm only, for the sine, I'm only going to be able to plug numbers in for this ratio that are between -1 and 1. And now think about this. Why is that the case? Okay? I'm dividing by the hypotenuse, correct? In a right triangle, what is your largest side? The hypotenuse, right? Okay? So you're taking a smaller number divided by a larger number all the time when I do opposite divided by hypotenuse, right? Okay? Well, if you have something small divided by something big, it will never be above 1. Does that make sense? Okay? So we can only type in ratios here that are between, what we're going to do is probably numbers between 0 and 1, but in trig we find out that it's numbers between -1 and 1. Okay? Same thing happens for the cosine function, because the cosine, the same exact relationship, say cosine of an angle spits back the ratio of adjacent divided by hypotenuse. The cosine inverse, you type in the adjacent divided by hypotenuse ratio, and it's going to spit back an angle. And because I'm still dividing by the hypotenuse, I'm always going to have a number between -1 and +1. Okay? Tangent's a little bit different. Tangent, you can type in any number. Okay? Because tangent is opposite over adjacent, and there's no, by comparison, we never know, is the opposite bigger or is the adjacent bigger? Does that make sense? So the quotient of opposite divided by adjacent can be any number from the real number line. So we're going to use that. When it asks us to find an angle measurement, we're going to use that idea there. Okay, and I'll show you the algebra that gets us an equation that we can work with. Now, the algebra that we're going to use is, because of a little bit of trigonometry, if I take, so when we have a equation that looks like, let's see here. Well, let's just do one of our problems. Let's start one of our problems, and then we'll get to the point of the algebra that we can grab the calculator there in a moment. All right, so if I look at this problem, the angle that they're asking me to deal with is this angle A, which is 29 degrees. Okay? So I'm going to say I'm focused on that angle. They're asking me to find C. C is the hypotenuse. And they give me this number here, which is the opposite side, right? Okay? So what we're going to do is that we are going to take which trig ratio uses opposite and hypotenuse? Sine. Okay? So we're going to take the sine function, and we're going to fill in all these things that we know. For the sine function, you always put the angle in. So our angle that we're dealing with is 29. I'm on the wrong question. What are we doing? Question. That was 19, wasn't it? I apologize. It's Monday. There we go. Looking for that one. Let me clean it up. Because that last one was just going to find a C, which was the hypotenuse. It was a distance, correct? And we should know how to do those. So let's do this one. All right. Apologize for that. All right. So this is the angle that we're interested in. What would 7 be in comparison to that angle? Opposite. And 18 would be hypotenuse. Is it okay with everybody? Which trig ratio, based off this angle, uses opposite and hypotenuse? Sine. So I would say sine, now of the angle, so I'm going to put x right there, is equal to opposite over hypotenuse. And just to prove a point here, I'm actually going to put a little gap here on the right-hand side of my equal sign, and you'll see why here in a moment. There's a word that I'm going to have to type in here, or insert here. Okay, so just like, and this is one of the reasons I talked about radicals, if I had that equation right there with the radical, I can't just pull x out, right? I have to use what thing for the square root of x to get x out? I have to use the inverse to get this x really kind of unlocked out of that radical, right? Okay? It's the same logic right here. That x is locked inside that sine function right now. And I can't get it out unless I use the inverse. Does that make sense? Okay? So what we're going to do is we're going to take the sine inverse of this side. And that's the way that we would write it algebraically. Okay? So much like the radical equation, if I squared the left, if I use the inverse of the square function on the left, I got to do that to the right, right? So down here in this trig equation, if I took the sine inverse of the left-hand side, I need to take the sine inverse of the right-hand side. Okay? Now, what I want to demonstrate with you is what happens, and this is where I'm going to grab my calculator, what happens right here. Okay? What happened up here when we squared a square root? Just drops down and gives me x, right? But the logic here that we're thinking is that this is only true for x values that are bigger than 0, because if x was negative, this would not happen. Okay? It's the same kind of idea right here. This is going to drop out when I take the inverse of sine of x. Basically, there's a cancellation that occurs here, and all we're left with is x. Okay, on the left-hand side. But it's only for a certain set of values. But for us, it's a nice set of values because we're only going to be looking at right triangles. So if I take the sine inverse of the sine of, I'm just going to say A here, okay? As long as A is between negative 90 and positive 90, and I got to be in degrees here to show this. So this, they're putting in 20 degrees right there. And what do I get back out of that equation or that expression? I get 20 degrees, right? So my input and my output equate all the time. Okay? Now that's only true for numbers between negative 90 and positive 90. If I make this go between, and this is what we learn in Trig, if I make this go between, let's go positive 90 and 180, once I start getting up to like 180, you see now I'm putting 154 in, and what's it spitting back to me? 26. If I plug 164 in, it's spitting back 16. Okay? Here's a question though. How does that number right there and that number right there compare? What are they to one another? What do you get if you add those together? 180, right? They're supplements. Are those supplements? Are those supplements? Okay. But what I'm trying to show you here is that between negative 90 and positive 90, and we'll prove this in Trig, that no matter what I put in, I get something out. Well, if we're working in right triangles, we're not even worried about negative 90 to 0. We're worried about 0 to 90, right? So if I'm worried about 0 to 90, do you see that no matter what number I put into this left-hand side, I get that number back? So when I insert A, I get A back. When I insert X, I get X back. Does that make sense? Okay. So there's a direct cancellation with that. And on the right-hand side, then, I'm left with sine inverse of 7/18. All we have to do now is take our calculator and type that in. Sine inverse, and now type in 7 divided by 18. Make sure you are in the correct mode. You want an angle spit back to you that is in degrees. So I spit back 22.88 degrees, and we round that to the nearest whatever they're asking for in the homework. Okay, so your calculator, you're going to have to type in 7 divided by 18. Hit enter, and now hit second. And now hit your sine key. So on calculators like this one, and when I say ones like this one, I also mean these red ones, or if you got a view screen on there that has 2 lines on it, you're just going to type it in directly. You're going to hit second, and then the sine key, and that will bring in that sine inverse notation. Okay, so sine inverse, and then I'll type in 7 divided by 18, close that off, we get my 22.8. If you have a calculator that only has one view screen line on it, you actually got to hit 7 divided by 18, hit enter, and then hit second sine, enter, and it'll spit back to 22.8. Okay, so 23. I like Desmos for the mere fact that there is a notation that is kind of an old world notation, and some textbooks talk about it. Some of your homework questions might pop up with it. The way I teach my trig class, we interchange them all the time. Sine inverse of x, cosine inverse of x and tangent inverse of x, they have other names. Okay? We can call sine inverse arc sine. Cosine inverse is arc cosine. And tangent is arc tangent. So if you ever see that notate, these mean the exact same thing. Okay? It's kind of the old world notation before technology. That's what they call them. Okay? And it has to do with arcs of circles, and I'm not going to get into the dynamics of why it's worded that way, but those do the same thing. So why do I like Desmos is because on your TI 8384, you got to hit second and find all those buttons and all that kind of stuff. On Desmos, I can actually type in arc sine of 17 divided by 8. Oh, what was it? It was 7 divided by 18, wasn't it? 7 divided by 18. And it gives me the 22.8. So you can see there, and that's a little bit easier than typing sine and then shift caret -1. And then I got to hit the directional key to get down to there, and then take 7 divided by 18, get the same thing. This is just quicker when I type in arc sine, arc cosine, arc tangent. Is that okay? So, let's do the next one. All right, so the variable is in this angle here. What would you call 9 in comparison to that angle? Opposite. And 7 would be adjacent. So which trig ratio are you going to use? Tangent. So I would say tangent of x is equal to opposite over adjacent, right? Okay. Now, tangent inverse is going to get this x to drop out. So tangent inverse, you come over here, tangent inverse. There's cancellation there, just like there was with the sine, dropping out just an x. And that's the exact value of x. If I gave you that in the number line and said, hey, go put tangent inverse of 9/7 on the number line, nobody's going to be able to do that, right? Okay. It's going to be a little bit bigger than 45 degrees. Should be a little bit bigger than 45 degrees. Take my calculator. I'm going to use arc tangent of 9 divided by 7, 52 degrees. Okay. I know, just because of my experience with trig, that if this was 9 divided by 9 or 7 divided by 7, it would have spit back exactly 45 degrees. Okay, so this number is a little bit bigger than 1, so this quotient should be a little bit bigger than 52 degrees. Does that make sense? Can we do that? All right, now, a lot of people are going to find out and they're going to say, okay, well, we go through all this algebra by hand right here, but really all I'm ever doing is I'm identifying, opposite and adjacent, so I know I can use tangent. And then I just go tangent inverse of opposite divided adjacent. So they circumvent doing this algebra. Does that make sense? Which is fine. If I get to this question here, okay, which trig ratio would you be using to deal with the adjacent side and the hypotenuse? Cosine. So a lot of people just jump straight to cosine inverse of 4 divided by 6.9. And that's fine. It gets you x. Does that make sense? However, if you're a person that doesn't, I'm not gonna fight you over. I'm not gonna argue with you because there's nothing wrong with it. You're gonna miss out eventually, and it might not happen until trig, that this confuses you when we get to trig. Okay? But if we focus on doing this algebra now, it'll make sense on the whole process. Okay? Much like if I were to start with 2x plus 5 equals, let's go, 13. Okay? And I jump all the way to, this is the first day of Algebra 1, and I jump all the way down to this. Could I have lost some people? Right? Okay? So doing a little bit of the algebra, subtract 5 from both sides, and then show the division by 2 will allow people to understand how I go from point A to point B. Same idea here using the inverse trig functions. Is that okay? All right. Does anybody have questions on this? Tomorrow, my plan is to make sure that we fully understand all of this. So we've been doing very dry, simple type questions. Find a distance, find an angle, make sure that we've refined that skill. Tomorrow we're going to move into utilizing this stuff in story problems. Okay. If we understand the algebra and the geometry, and then set up the algebra, the story problem should not create a problem at all for us. Okay. So that's the plan for tomorrow. You still have 8.3 open, but I also put another assignment for more practice, 8.3 assignment 2. That'll be due on the 10th. You guys can work on that stuff now.